All right, let's talk about this concept of the mole. This is usually a topic that's pretty challenging for students, and I don't really know why. It doesn't have to be. A mole is a pretty simple concept because a mole is just a number. It's actually, well, it's a word that represents a number, I guess I would say. So just like the word dozen represents the number 12, the word mole in chemistry has its own number. That number is this. 602 with 21 zeros tacked onto it. That's a huge, huge number. We always simplify that down with scientific notation to this 6.02 times 10 to the 23rd. You need to commit that to memory or have it written down. We call that Avogadro's number. Avogadro was a chemist in the mid-1800s, and we'll talk more about him, but I do have a picture of him because he's just such a funny looking guy. I always like to show this. What a weirdo. Anyway, so Avogadro's number is used in chemistry for lots of different things, primarily counting numbers of atoms or molecules or particles. So let's figure out how this works. So here's a question I'll start you with. You know that a dozen means 12. So if you have a dozen eggs, what's the mass of that? Well, I don't really know the answer to that because the answer would depend on the mass of each egg, right? But here's what you can say for sure. The mass of a dozen eggs is gonna be pretty different than the mass of 1 dozen bowling balls, right? And that's because the mass of an egg is really different than the mass of a bowling ball. So you can expect the mass of 12 eggs to be quite a bit less than the mass of 12 very heavy bowling balls, right? And that's the way it works in chemistry too. So just like you couldn't really equate the number of grams of eggs to bowling balls, like lithium atoms, for example, are so much smaller than lead atoms that if you had a dozen lithium atoms, it would have a much smaller mass. You know, each lithium atom is only 6.941 on average atomic mass units, where a lead is this big, fat, heavy atom at 207.2 atomic units. So they're just atomic mass units, excuse me. So they're just such different sized atoms that you can't expect the same number of each to have the same mass total, right? And so just like you can't expect 12 lithium atoms to have the same mass as 12 lead atoms, you can't expect Avogadro's number of lithium atoms to have the same mass as Avogadro's number of lead atoms. We're just substituting the word dozen for moles, right? And a different number too. Okay, so that brings us to this concept of molar mass. So if you were to have Avogadro's number of atoms of a single element, you would call that the molar mass. It's the mass in grams of 6.02 times 10 to the 23rd atoms of that element, right? And it's equal, and this is where it gets easy actually, it's equal to the element's atomic mass, but it's reported in grams instead of atomic mass units. And so when you look at the periodic table, you have these squares where these element symbols live. So this one's aluminum, and the atomic mass is listed down here. This is the average weighted atomic mass. We're now going to call that the molar mass in grams. And so the 26.98 AMU, that is now just 26.98 grams. That means that if you had Avogadro's number of atoms of aluminum, if we had that many atoms of aluminum, then on the scale would say 26.98 grams, okay? So let's calculate some molar masses. This is pretty easy. So a lot of times we're looking for the molar mass not just of a single element, but of a compound. And it's really just as simple as looking at the compound formula, seeing how many of each atom are present, and then summing up the atomic molar masses of each element. So if we had this compound here, CO2, okay? we know that the chemical formula tells us basically how many atoms there are of each element. So we have a single carbon and 2 oxygens. So here are the symbols from the periodic table. We have, each carbon is 12.01. We're going to add that to 2 masses of oxygen, each at 16.00. And then on your calculator, you just add those numbers up and make sure that you report your final answer using the lowest number of decimal places provided, which is 2 in all these, so that's easy enough. And then that's pretty easy to do. With a compound that might be a little bit more complicated, like let's look at K3PO4. Although that's not really that much more complicated. It's not complicated once you know how to do this stuff. The mass of each of these individual potassiums is 39.10, and we have 3 of them, right? So instead of writing it out 39.10 plus 39.10 plus 39.10, I'm just gonna multiply this by 3. Oh yeah, and then we're going to add that to the mass of 1 phosphorus atom, which is, let's see, 30.97. And then we've got 4 oxygen atoms to take into account here. So I'm just going to multiply the mass of 4 oxygens, and that is 4 times 16, right? There we go. And of course, all of the numbers that we're adding together all have 2 decimal places, so we're going to report our final answer. Doesn't matter how many significant figures are there with addition. Remember, we just want to carry the lowest number of decimal places in our final answer. Okay? H2O, if you're, now it's probably getting easy for you, but the mass of a hydrogen is 1.008, and then we have 2 of those, right? And then we're going to add that to the mass of just a single oxygen, which is 16 again. And so, you just add them up. Again, here we're limited in our decimal figures by 2 decimal places. There's some stuff to look out for with decimal points, because some of the molar masses from the periodic table have 3 decimal places, and some only have 2. And then some have 1, which we'll do down here with lead. Copper 2 nitrate, this is where you have to be good at taking the name and putting it into a chemical formula, and then from the chemical formula you can get the molar mass. But you can see how important it is to get the chemical formula right, because the subscripts, if they're wrong, you're going to have an incorrect molar mass, which can throw all of your calculations off down the road. So we would just turn this into a formula. Here we have Cu with its oxidation state of +2, which is going to be end up being the subscript for our nitrate ion, which we'll put in parentheses with a 2. Now, here is where you have to remember that the outside subscript, if you have a subscript that's outside the parentheses, that is going to distribute by multiplication to all of the subscripts inside the parentheses, right? So here we've got a single copper to account for, so that's 63.55, and we've got 2 nitrogens. Each are 14.01, and then we've also got 2 times the 3 is 6 oxygens, right? So the biggest mistake people make is getting the formula wrong, and they don't have the right subscripts, and then they don't have the right number of atoms. They've counted them up wrong, and you get the wrong molar mass. Now, with lead and some other elements out there, we have a kind of a funny thing. The formula here for lead 2 carbonate is and +2, carbonate's 2, PbCO3. Okay, so lead has its own molar mass of 207.2, okay? And so you'll see here that some of the masses from the periodic table have just 1 decimal place. That means that your final answer is going to be limited to the lowest number of decimal places, which in this case is going to be just 1. We'll go through this one. And then we're going to add that to just a single carbon, 12.01, and then we're going to add that to 3 oxygen masses, each at 16, so 3 times 16. Okay, so you can see that our carbon is 2 decimal places, our oxygen is 2 decimal places, and our lead is only 1 decimal place. That means that when you add this up and your calculator spits out an answer, you've got to round the decimal to just 1 decimal place. Okay, that's it. I hope this helps. It's an important skill that you got to get right. It's one of those things that can throw you off in a big way, especially when you have a long problem to get through. So we'll do lots of practice with these. Thanks.